Well, hey, it's Dr. J, and I'm back with the fundamental theorem of calculus. Dun, 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 dun. Today we see the prequel to the episode that you've already witnessed. Today we're going to do part one of the fundamental theorem of calculus. It starts off almost identical. Let f be a continuous function on the interval AB if capital F of x is the integral from a to x of f of t dt. Notice the variable for the integrand is now t. It actually doesn't have to be t, it just has to be some other substitute variable other than x. So you can use u or v or w or s, or I like to use t. Then f prime of x is just equal to f of x. Now this gets a little bit confusing because we're using two different cases of the letter f, lowercase and uppercase. I do have some alternate forms that I'll show you that maybe are a little less confusing. And then where is x? X is any real number between a and b. Inclusively, so it's like this. X could be anywhere between a and b, inclusive of the endpoints. Although I won't give you any examples where x is actually equal to a, but that's still officially the definition. So there you go. That is the prequel to the fundamental theorem of calculus. This is the backstory. This sort of tells us where the fundamental theorem part two that we've already seen came from, right? This is the evolution or the creation story of the fundamental theorem. The notation is a little bit weird. Basically what this says, if you think about it, is it basically describes a relationship that we already know between integrals and derivatives, which we kind of already suspected. That was, I mean, I know my Star Wars story was pretty cheesy, and I have to admit I watched it a couple times, and I was a little embarrassed. But you know, I appreciate your sympathy. But didn't you kind of already suspect it, right? I mean, even the stuff about Luke and Leia being brother and sister, ooh, they kissed and stuff like that. Like, we already kind of suspected it, right? And so we already knew that there was a relationship between integrals and derivatives. We fully fleshed that out at the beginning of chapter 4. And this theorem, we call it the fundamental theorem, but it's really a pinnacle theorem. It's a culmination theorem of sort of the end of the road that we've already been traveling for a long time. So all this basically does is give us a well-defined relationship, between derivatives, that's the f prime, and the antiderivative, also known as the integral. Let's see an example. So we'll start with capital F is the integral from 4 to x of t to the 5th dt. So before I erase this, just to make everything clear, this is our capital F, yeah. This is our A. A is 4. There's our x. And then our f of t dt is right here. And so basically, what does this theorem say? It says if you take the derivative of a function that is already written as an integral, this is your f of t. I'll put that in a cloud here. There's your f of t, which is just t to the 5th. You're going to love this homework if you haven't done it already. I noticed a few of you didn't even wait for me to make the video. You just got right into it and did the homework. Then, by FTC1, Fundamental Theorem of Calculus, Episode 1, f prime of x is x to the 5th. I mean, it really is that easy. You just replace the variable t with the variable x. When I first saw this theorem, much like you know, I learned this in opposite order. So I was first exposed to Fundamental Theorem Part 2. And then I saw Fundamental Theorem Part 1 and I went, what the, you know, what is that? You know, what's going on? I mean, here's the idea. You know, this is sort of the background or the backstage. You know, this is how the sausage is made. You know, this is where all the magic happens there. The idea is this, okay? Suppose that you just took the integral from 4 to x of t to the 5th, all right? Well, let's go ahead and do that, right? Let's go ahead and do that because we actually know how to do this, right? You would get 1/6 t to the 6th, right? You remember the rule? You just add 1 to the power and then divide, or you could write it as t 6th over 6. Yeah, same thing. These tomato, same thing. And then your a is 4 and your b is essentially x. So using the Fundamental Theorem Part 2, which is kind of why you need to see Episode 2 before Episode 1 would make any sense, you would get x to the 6th over 6 minus 4 to the 6th over 6. Now, I don't really care what 4 to the 6th over 6 is. It's just a constant. Yeah, it's just a constant. So that means that this function, the integral from 4 to x of t to the 5th dt, can be rewritten as x to the 6th over 6 minus 4 to the 6th over 6. So, if I take the derivative, I would bring the 6 down in the front. I would subtract 1 from the power. All right, remember this is now chapter 2, right? Derivatives. Divided by 6 minus the derivative of a constant becomes 0. And then I would cancel the 6's and simply get x to the 5th. So that would be the long grueling way to, exhaustively determine what the theorem already tells us. So we already knew this. With a silent K by FTC1. Yeah. So a theorem is just sort of like a conclusion that you can draw without actually having to do the work. That's the power of a theorem. All right, so that's example one. Sort of beat around the barn a couple times. We do have some alternate forms of FTC1, Fundamental Theorem of Calculus 1. You may also say, so we'll call this alternate form number 1, if capital F of x is the integral from a to x of g of t dt, I prefer this version because it doesn't confuse the capital F and the lowercase f. Then the derivative of f, and this is really good if you're just listening, because when I say f, I don't have to specify whether I'm talking about capital or lowercase, is just equal to g of x. So essentially, you take the x, you plug it into the t, and then there's your final answer. And then you ignore a. A is a constant, so when you plug in the a, its derivative. Remember, the fundamental theorem part 1, you are taking the derivative of an integral. And so that's part 1. Alternate form 1. There's another form that I use occasionally. That's the d dx form. The derivative with respect to x of the integral from a to x. And then I put the f on the inside of the integrand. This one's kind of a hybrid of number 1 and the original theorem that I proposed a minute ago. This one's really nice too because it only uses one letter, f. Right. So this is just the alternate notation for prime. So instead of saying f prime, you're saying d dx, derivative with respect to x, which is really what the prime meant, all along, going all the way back to chapter 2. So there are your alternate forms. I guess we could do another version of, let's do one of each, I guess. Let's do one of each. Example 2, 2 parts. Let's say part 1 will be, maybe I'll use here, let me use letters. Part A. Let's do f of x is the integral from -1 to x of the square root of t cubed dt. Find f prime of x. And then part B, find the derivative with respect to x of the integral from -1 to t of t to the cube dt. I really like doing the same problem 2 different ways. They should give you corresponding answers. So you take the x, you replace it with the t, you ignore the constant, and your answer is just this simple: the square root of x to the 3rd power. And that's it. I mean, it almost seems too easy. It's a theorem, so you don't actually have to do the work. The theorem does all the work for you. All right, this one's nice because it's just one line, yeah, and it's the same exact answer. It says the derivative with respect to x of the integral from -1 to x of the square root of t cubed with respect to t is just the square root of x to the third. Again, the -1 is a constant. Because the derivative, remember, you're taking the derivative and that's a constant, so that just becomes 0. So, I mean, technically there is a, -0 here on both of these answers. Nobody ever writes the -0. I mean, I do, but I'm weird, I sometimes write things that other people would ignore. Okay. Next, we are going to what's called a corollary. I might have spelled it wrong. I have unresolved issues with double letters. When I was a child, growing up in California, we learned all 50 states, and we learned how to spell all 50 states. We learned the capitals of all 50 states. I'm not sure I still remember all 50 capitals, but at one point in my life, I knew them all. And the spelling of all 50 states. One of those states that we had to learn, as a young person here in California was California, which, is relatively easy. It doesn't have in double letters or anything, but Mississippi, Mississippi. And it damaged me for life. My spelling, if it wasn't for internet Google spelling, I would probably make a lot more mistakes than I already do. So I'm confessing that this might be spelled wrong, and I just blame it on Mississippi because I always like to put two of the same letter, Corrollary, because of Mississippi. It's probably spelled wrong. A corollary is like a... when they make like an offshoot of something, like they take a show and they make a side show that kind of emanates from that show. That's what a corollary is like. Yeah, it's like one of those side movies. It's not really in the canon of the story, but it's an offshoot, a breakaway. There's a Hollywood term that I'm missing. And it says the integral from b to a of f of x dx is equal to negative the integral from a to b of f of x dx. So this is a corollary to FTC Part 2, the one we started with. It seems pretty obvious, I hope. If you switched the bounds, the lower and the upper, and did it from B to A, how bad could your answer be? Well, it would just be the opposite, the negative of the same integral from A to B. It's kind of like you're integrating backwards, or you can even think of it as upside down. Either way, you get a negative. So example 3. Let f of x be the integral from x to 3 of 1 over 1 plus t to the 4th dt. Find the derivative, f prime of x. Well, we're going to use this corollary. So this is our A, and this is our B. So we're going from B to A. So that will be equal to negative the integral from 3 to x of 1 over 1 plus t to the 4th dt. And then we'll do the FTC, Fundamental Theorem of Calculus 1. You're going to get 1 over 1 plus x to the 4th. And that's your final answer. If you're afraid this negative is going to fall off, you can put it up with the 1 like that. Or you could just leave it out in front. It's up to you. So we're using the corollary to Fundamental Theorem Part 2, which basically says if you switch the lower and the upper limit, you just change it to a negative, change the result to a negative. And then we're using the Fundamental Theorem Part 1 to complete the problem. You could just combine this all together and jump right to here if you like as well. If you already know the result, that's great. Well, that's the end of the basic examples. We've got a couple more elaborate examples that involve multiple steps. Find the derivative with respect to x of the integral from 2 to 8x of the square root of t plus 1 dt. I frequently go back and forth between the two different alternate forms. I'm actually going to do this one step by step. I'm going to do this one step by step. So, the x is now an 8x, right? The lower bound is still a constant, but the upper bound is not. It's a variable expression, 8x. So we can ignore the constant, yeah, because the derivative is 0. There's our official formula for it. d dx of k is equal to 0. So that's going to be 0. Remember, we're taking the derivative of this. However, we can't ignore the 8x. The 8x replaces the t. But then we have the chain rule. If the bound value is not just x. So the boundary value is not just x. So the chain rule says you need to take the derivative of the boundary value. And the boundary value, or it's also known as the upper limit, or upper boundary, means the same thing. Okay. The top. Although it's not really the top, it's more the right-hand side of it as you're moving from left to right. I guess it becomes the top when you evaluate it, right? When you plug it in, it becomes the top of something. So you have the square root of 8x plus 1 times 8. You could type it in like that, although I would probably move the 8 to the front just because it looks nicer. But if you've already typed it this way, as long as you have a multiplication dot, and as long as the square root symbol doesn't cover the 8, that would be bad. So one of the reasons why we put the 8 out in the front. Sorry about that. I forgot to turn my phone off. Nobody ever calls me unless I'm filming. So there we go. That's our result right there. Let's do another one of these. These are kind of fun. I don't know. I mean, we're on the home stretch here, so I hope you're enjoying the experience. If you're just waiting for it to be over, it will be over soon. All right, same kind of question. We have the d dx, the derivative with respect to x of an integral. Again, we can ignore the lower bound because it's a constant. We can replace the t with x squared. But then we have to multiply by the derivative of x squared. And I'll just write chain. Or sometimes people say CR, chain rule. So that'll be x to the 8th times 2x, which combines to be 2x to the 9th. There you go. Not too shabby, huh? I think we're almost done. This might be the shortest video of the entire semester. It's a prequel, so it's a very short one. It's not one of those 3-hour-long, exhausting lessons by Dr. Jordan. All right, well, let's wrap this up then. A couple more, and we'll be good to go. Let's go back to the original form. F of x is the integral from 6x to ln of x of e to the 9t dt. So we can't ignore either of them. We can't ignore either of them. That we need to use both of them. So let's find f prime of x. So that's going to be e to the 9 ln of x. I'm using double parentheses. I could probably get rid of one of the sets in a minute, but times the derivative of ln of x minus, we can't ignore this one now because it's not a constant. It's a variable expression, 6x. So that's going to be e to the 9 times 6x times the derivative of 6x. So e to the 9 ln of x times 1 over x. That's one of the ones you should just memorize. The derivative of ln is 1 over x. And that'll be e to the 54x times 6. Derivative of 6x. I would probably clean this up a little bit. 9 ln of x over x minus 6e to the 54x. So this section, or this is the tail end of the homework for the fundamental theorem. I bundled both part 1 and part 2 together in reverse order. So you use part 2 first, and then you'll finish off the homework with part 1 of the fundamental theorem, and you'll see that your answers start to get a little bit more complicated, I guess is a word, but they're not really complicated. They give the impression, the illusion of complexity. To the untrained eye, this might look complicated, but to you, the well-trained observer, this should just look like everyday bread and butter. Yeah, this is basic calculus at this point. I've run out of examples. So I've taken you all the way to the mountaintop. And I only have one more to do today. And it's again using this alternate form. The integral of x to x cubed of 5x squared plus 5t squared plus 7 dt. Now this is one that we actually could have done in episode 2 or part 2. Right? We could have done this. So because it's my last example, I'm going to go ahead and do the whole thing. All right. So watch. First, right, I'm going to take the integral of this. And I'm doing this intentionally because it combines the FTC2 and FTC1 and basic facts of antiderivatives. It's also the kind of thing that I really emphasize for a final training, final preparation to see if you're really understanding. It brings together almost everything that we've learned with a very simple function. So we're going to go 5t to the third over 3. Yeah, that's the basic antiderivative plus 7t. All right, so those are your two basic antiderivatives. Then you do the boundaries. So this is your A and this is your B, yeah, from A to B. And then you use FTC2. Fundamental Theorem Part 2. So you plug in A and B. You plug them in. So you get 5 x to the third over 3 plus 7 x to the third minus, use some extra brackets, 5 x to the third over 3 plus 7x. So you do f of b, you plug that in first, that's the upper bound, minus you plug in a, the lower bound, the lower limit, and then you use some kind of a parenthesis or a bracket. It really doesn't matter to make sure that that minus is, affecting the entire second half of the expression. So what does that mean? So now we have f of x is 5x to the third over 3 plus 7x to the third minus 5x to the third over 3 minus 7x. Let me try to write that a little bit better. I guess I didn't do a very good job of that. All right, that's fine. Okay. So this is 5x to the 9th over 3 plus 7x to the third minus 5x to the third over 3 minus 7x. So now the derivative is 9 times 5 which is 45 x to the 8th over 3. So you see how this kind of reviews everything in one problem? 3 times 7 is 21 x to the 2nd. We're taking derivatives now. Chapter 2. Minus 3 times 5 is 15 x to the 2nd over 3. And then remember, the derivative of a linear term, 7x, is just 7, or whatever the slope is, right, or the constant. It's not 0. Sometimes mix those up. The derivative of a linear is different than the derivative of a constant. So your final answer, 45 divided by 3 is 15 x to the 8th. 21x squared minus 5x squared is going to be 16x squared. I didn't really write that, but this 15 divided by 3 becomes 5. So 21 minus 5 is 16, and then minus 7. And there's your final answer. So I hope you enjoyed this these last couple episodes. The fundamental theorems are interesting because they're fundamental, but you don't learn them until you're practically done with this course. My next video will be possibly the last video of this course. Quite probably the last video of this course. I'm going to do one final business math application to finish off this experience and start talking about the final exam, which is coming next. But until that day, keep working hard, finish all your work. We're almost there, taking you all the way. One more video to go. Until then, I'm Dr. Jordan, and I'll see you on the internet.